Okay, now everyone. Yeah, let's get started. So first of all, just reminder, our homework one will be due on this. Homework two will be due on this Friday. So please leverage the office hours as much as possible. If you're still have some problem in implementing your algorithms, right? And please try your best to finish that in time. I received a request asking that if we can extend homework homework two to next week, and usually we need to wait until we receive a lot of agreement requests, right? We cannot do that for just one or two requests. Otherwise, it won't be fair to other students who can commit to the deadline, right? And of course, if you have some personal issue, like you have a health issue, you have some emergency, and if you have some doctor's notes or other things, right, like witness letters, yeah, we can definitely consider personal extension. But other than that, we'll still suggest everyone to try to stick to the deadline and also try to leverage the office hour as much as possible. And also, I think next Friday will be our due of the midterm project report. So please don't forget to submit your report and tell us what you have done for the course project. Okay, any questions so far? Okay, great. So today we're gonna wrap up the perception. So and then we'll introduce the next topic called support vector machines. But to motivate support vector machines, we're gonna first illustrate the sample complexity bound. I mean, we're going circle back to the computational learning theory we have previously discussed, and we'll see that in a more general sense, what will the sample complexity can determine the performance of the generalization error, and in what kind of using what kind of strategies can we maximize the generalizability. Okay, so let us first try to wrap up the perception. So the remaining thing about perception is about practical variance, right? So we previously talked about the standard framework of perception. We know that it is online learning algorithm. It is a lazy learning in that only when you make a mistake, you update the model, right? If you can correctly predict the current example, you won't need to do anything, right? And we talk about theorem. We talk about if the data is linearly separable, how many updates or mistake at most your perception algorithm will make, right, to convergence, right? And but in practice, we need to consider more complex situations, right? That is, the data set is really not linearly separable, right? In that case, we don't want to run your perception forever and ever, right? You want some like a more robust version, more practical version, right? So this is standard algorithm, right? Initialize our perception algorithm, the weights to be 0, and we'll go through big T epochs, right? Each epoch you're gonna pass through the whole data set, right? And every time you're gonna random shuffle the examples and then look at every example sequentially, right? If the current model can correctly predict the current example, you don't do anything, right? Otherwise, you're gonna update the model parameters following this rule, right? So I'm not gonna, yeah. And then we started talking about the first variant is called margin perception, right? So we kind of start thinking about, given a linearly separable data set, and you might have like infinite many hyperplanes which can perfectly separate all the positive examples from negative examples, right? Then a natural question would be, which hyperplane do you think will generalize the best, right? And of course, we have a very good intuition. We believe that the hyperplane which has large margin will generalize better, right? We give a little bit of analysis. The rationale here, I want to repeat again. The larger the margin of the hyperplane, Remember, the margin means the minimum distance between the data points and the classification boundary, right? The larger the margin, meaning that the further away your classification boundary is from the data, right? If you choose a classifier who has a small margin, like H2, it brings a risk in that the classification boundary can easily cross the high density regions of those examples, right? For example, H2 here, we know that it has a small margin. That means we'll look at the position of the boundary. H2 passes through high density regions for positive examples and high density regions for negative examples, right? And then the risk of misclassification increases dramatically because H2 passes through this high density region, right? That means on both sides of H2 here, you are highly likely to meet positive examples, right? Of course, the positive examples here definitely will be wrong, right? I mean, will be classified wrongly by H2. And similarly, H2 passes through these high density regions for negative examples as well, right? And on both sides, you got much higher chance to meet negative examples. And this side, when you see the negative examples, H2 will definitely make a mistake. So that means the small margin can increase the risk that your classification boundary passes through the high density regions, and then you got a higher chance to misclassify examples on the nearby the boundary, right? On the other hand, if you have a large margin like H1, right? So because it is far from both the positive high density regions and negative high density regions, right? So it's highly unlikely that, okay, you have some positive examples appear on this side, right? Because it's low density regions, right? Your chance of meeting such a positive examples and make a mistake is much lower, right? And similarly, it's highly unlikely that you're gonna see some negative examples here because it is a low density region for negative examples, right? So your risk or your chance of making mistakes in predicting this negative example is low as well. That's why we always encourage finding a classifier or hyperplane which has a large margin. So now let us integrate this idea into the development of our perceptron variant, right? So we'll call it margin perceptron. So in the standard perceptron, right, we'll only update our model parameters. By the way, updating the model parameters just means you're going to adjust the position of the hyperplane, right? So we make updates when the prediction is incorrect, and we use this inequality to check if the prediction is incorrect, right? But now we're going to change the condition which trigger us to adjust the hyperplane. Right? How can we change that, right? We pick up a positive eta, and then we check, I mean, after seeing every example, right? We just check if, remember, this is distance, right? This is definition of distance. If the distance between xi and our current hyperplane is less than this given eta, then we're going to model our we're going to update our model parameters. Okay. So, of course, if you wrongly classify example xi, this guy, the numerator will be negative, right? Right? Because we know that if you make wrong prediction, this product, the label and the score must be negative, right? So this condition will satisfy, and it will definitely adjust the hyperplane, right? On that, however, in addition to that, right, we cannot restringent the condition, right? Even your prediction is correct, but if this distance is less than eta, I'm gonna adjust the position of hyperplane as well. Okay. So suppose we can do this, and we can use this condition to determine whether we're going to update our model parameters or not. And suppose we can converge eventually. So where will be our separating hyperplane? Or what kind of properties our separating hyperplane will have? Any thought? Let me repeat this question, right? Suppose now we change the condition when we update our model parameters, namely adjusting the hyperplane, right? And we, after a finite number of updates, we converge, meaning that this condition will never be triggered again, right? We got a hyperplane, right? So what kind of properties will this hyperplane have? Yes. Yes, exactly, right? So if we run this and until convergence, right? Let us assume it will converge, right? Then we know that for every training example, we have the distance to the hyperplane is at least eta, right? It's no less than eta. So that means the margin will be at least eta. Right? Does it make sense? Right? So that's how we inject some constraint on the margin, right? We pick up some eta and require our learned linear classifier of separating hyperplane whose margin is at least eta, right? This is called margin perceptron. Okay. And why is this a good idea? As we just mentioned, right? We believe that a classifier with large margin will generalize better, right? So by setting appropriate eta, we're going to try to enforce our perception learner to find a large margin classifier whose margin is at least eta. Right? Any questions so far? Yeah. So what's the possible defaults of this method? Yeah. Could anyone give me some critical thinking? Okay. What kind of problems might be caused by margin perception? Choose the what? Yes, exactly, right? So here we give them more flexibility because we can set eta, right? But imagine that if your eta is too big, it's bigger than the margin of whole data set. Remember, the margin of the whole data set means what? It means the maximum possible margin that is separating hyperplane for that data set, right? If eta is bigger than that, then your algorithms will never converge, right? And similarly, if eta is too small, that might be not general enough, right? So you have to devise a kind of strategy to choose a proper eta. Right? One possible strategy will be, okay, let me just start with a very small value of eta. If they can converge, say after a maximum number of epochs, and just try to increase eta by some number, right? You do it until after many epochs, you still cannot converge. So anyway, running margin perception, you need to carefully choose eta because it is the minimum margin you request your linear classifier to have. Okay, so the first practical variance of margin perception. The second one is called the voting or unreging perception. Okay. So in this case, we need to face a situation where your data set is not linearly separable. After all, assuming your data is linearly separable is a very strong assumption. Right? And For example, this data set, you can see that most examples might be linearly separable, but there are always some outliers which are not linearly separable. Right? In that case, how can we drive our perceptual learning? Right? One intuitive idea will be, okay, why not we just find a separating hyperplane which makes a minimum mistakes, right? For example, I only make 2 mistakes in predicting these 2 positive examples, right? For the others, I can correctly predict. Then that's a good one, right? However, finding a hyperplane with the minimum mistakes is a very difficult in terms of algorithm efficiency. It's an NP-hard problem. Then in practice, how can we address that? We don't want to really enumerating all possible hyperplane positions than to find the one who has the minimum mistake. So we got 2 variants. The first one is called vaulted perception. This is very similar to a ensemble learning we have previously discussed. Right? Remember, ensemble learning means that, okay, I have a set of classifiers, right? And when I do the final prediction, I'm going to aggregate the prediction of each classifier, right? And then count their votes, right? Pick up the final vote for positive or negative, right? So here's the algorithm framework for vaulted perception, right? We got the same setting for the standard perception. Suppose we have a training data set, D, right? We got labels to be either -1 or +1. We initialize our weight vector to be 0, right? And here, we add a index M, starting from 0. So you can view it as this M indexes a set of different hyperplanes. We're going to run our perception and then record all the distinct linear classifiers. Right? Remember, this is how the perception is running, right? We keep doing that. We keep testing if our current prediction is right or wrong, right? If it's right, we just keep the current classifier, right? And until we meet the first incorrectly predicted example, we're going to adjust our hyperplane. Then we switch to the next hyperplane, right? So the vaulted perception essentially is to track all the possible distinct weight vectors during the perception running. And then I'm going to aggregate the prediction by those distinct linear classifiers together. That's the basic idea, right? So now let us look at the algorithm. How can we modify it and track them, right? So again, we're going to run the whole algorithm for big T epochs, right? And big T is chosen by you, right? And then for each epoch, we're going to random shuffle the algorithm and look at random shuffle the training set and then go through every training example, right? If you make a wrong prediction, that basically means, okay, the current model should be changed, right? Then we're going to construct a new model, right? The new model whose weights are obtained by this updating rule, right? At the same time, you're going to store a new weight vector, right? That's why we increase M by 1, right? And then you set the life cycle variable Cm to be 1. That means I'm going to start to count the life cycle of a new weight vector or classifier. If your current model can correctly predict the current your example xi, yi, that means I don't need to change my model, right? And then I'm going to increase the life cycle by 1. So Cm here is the life cycle, or you can view it as count. Right? It roughly records how many examples in total your current classifier can correctly predict, right? And the more examples your current classifier can predict, the longer the life cycle, right? And the more important of that classifier. Because we believe that it can better predict those training set, right? And in this way, we can see that actually we just keep recording or keep tracking all the possible distinct weight vectors, right? And now for each distinct weight vector, we record its life cycle, namely how many examples it passes through, right? And eventually, after you finish running all the big T epochs, you can imagine like we got K distinct classifiers, right? And each classifier has its own life cycle, C1, C2 to CK, right? We actually have collected an ensemble of linear classifiers. Does it make sense? Any question? And then during the final prediction, right, it's very similar to ensemble learning, right? So we use each distinct linear classifier to make prediction. So this is our label, right? Then we assign a vote by the life cycle. And eventually we're gonna compute the total vote for positive prediction and total vote for negative prediction. Which one wins, we're gonna output the corresponding label. So this is called voted perception. Any questions so far? This is true for forever, right? Okay. So now I want to ask, what's the problem of this voted perception? Any thought? You just give me a random guess. Okay, one immediate cons, which I can say, is that you have to explicitly record those different weight vectors, right? And also there are cons. You have to calculate them, right? You have to track them, right? And if you have a super large data set, you can imagine you got a great many distinct weight vectors, right? And there are cons. So it's kind of like memory inefficient, right? So is there any, even better way that you don't need to explicitly track all distinct weights, but you can still do this? That leads to our second variance. It's called enriched perception, right? It's extremely simple, right? It's extremely super simple modification of the original perception, but it's very smart, right? So let us look at the algorithm first one. So the only change in the enriched perception is that, okay, I'm not gonna track W. Instead, I'm gonna introduce a so-called average vector and initialize as 0 as well as W, right? And then we just follow standard perception. Like if your current weight can make the correct prediction, you do nothing. Otherwise, you update your weight accordingly, right? But after saying every example, you're gonna add the current W into A. That's it. And then you're gonna return A rather than W as your model parameters. Then you use this A to make prediction. That's it. Let's see why this is still doing some kind of ensemble classification by linear classifiers, right? So you can see that A is essentially the weighted summation of every weights, right? Multiplying with this count for life cycle. Why? Yeah, let me write down. So from a previous algorithm, right, we see that we explicitly track the set of distinct weight vectors and their life cycles, right? And here I claim that your A essentially is just the weighted summation of all the distinct weights multiply with their life cycle. Why is it true? Why is it true? Yes, exactly, right? So just look at where we put the operation on A, right? So A is like, okay, no matter you make a correct prediction, wrong prediction, after you see every example, you just add the current W into A. That's it, right? So imagine that, okay, if your W still survives after seeing this example, you're going to add the same W into A, right? So keep doing that until your W does not survive. That essentially is to say you add A into the life cycle many copies of the same W, right? Does it make sense? Right? And then once your life cycle ends, meaning that your current W make a wrong prediction, you got a new W, right? But you're going to still add this new W into A. And you just keep doing that until that the new W's life cycle ends, right? So you can see that A essentially has aggregated all the distinct weights in running perceptron and also their life cycles. Right? And then when we make a prediction, we'll just use this aggregated weights to make a prediction, right? Because A equals to this guy, and you do dot product with X, essentially doing this, right? Any question? Yes, this is a very smart strategy, right? And it doesn't explicitly track all the possible different weight vectors and their votes, but they're implicitly doing that. Okay. So this is extremely popular, right? If you want to use your perceptron to for your own problem, right? Try to use average perceptron. Right? But there is still a tiny bit difference between the voted perceptron and the average perceptron. Right? The major difference comes from the prediction step. So in a voted perceptron, right, we use every distinct weight vector to make a prediction. First, either either positive one or negative one, right? And then we just vote, we just count the vote for that label. And then we look at which label has a larger total vote, right? But for average perceptron, you can see that because this guy is A, right? This guy is A, right? So when you do the voted prediction, they're essentially vote on the score, not the label. And the score is actually this guy, right? W transpose X. It's a real number. It's a continuous number. It's not a positive one, right? And then we're going to look at whose score, the scores for the voted score for the positive label is bigger than the voted score for the negative label. Then we predict as positive. Otherwise, we predict as negative, right? So you can see the object you vote for is different. Right? For the voted perceptron, well, we just vote positive one or negative one, right? And for the average prediction, we vote to the score. And then we just look at, okay, the total score for positive label and total score for the negative label. We just look at who wins who, right? And some concrete example, right? Suppose I got 3 distinct weight vectors, right? The score of the first weight vector to predict X is S1, S2, S3, right? And the votes are the same, C1, C2, C3 are 1, right? If we do the average prediction, that means we're gonna just vote every score by their C values, right? And then add them together, we'll look at if S1 plus S2 plus S3 is non-negative or not, right? If it's non-negative, then we predict it's positive. Otherwise, predict negative. But for the weighted perception, we first convert those scores into a label, right? Either +1 or -1, right? And then we just look at who's how many positive labels do we have, how many negative labels do we have, and pick up the one who has larger votes, right? Any questions so far? Okay, great. So just be careful about the subtle difference between the two versions of the perceptions, weighted and average perception. Okay, so now we have finished the introduction of perception. So perception essentially is an online learning algorithm. It is very widely used and easy to implement, right? And it uses some additive updating rule to the weights, but we have seen why their updating rule is rational, right? And it has nice geometric interpretation. And we went through the Mr. theorem, and we talk about several practical variants, right? Now here, we request you guys to be able to implement the perception algorithm. Okay. So now, okay. So in the next stage, we're going to talk about agnostic learning and VC dimension. So we're going to, from this discussion, right, we're going to motivate a new linear classifier learning algorithm called support vector machines. So what is agnostic learning? So if we can recall what we previously discussed about computational learning theory, right? We're assuming that, okay, your learning algorithm is powerful, and no matter what kind of training set you give the algorithm, you can always find a hypothesis which can perfectly fit the whole training set, meaning that your training error is always 0, right? And of course, we know that won't be practical, right? Because you cannot guarantee your algorithm always gives a 0 training error, right? Especially when your data set is large, right? So agnostic learning wants to answer the question, right? What if I cannot guarantee 0 training error? Can we still get the bound of the generalization error? Okay. So remember, we have some previous conclusion that if your number of examples is bigger than some lower bound, then with high probability you got your learned classifier whose generalization error is less than some given threshold, right? So can we obtain a similar conclusion in this case, even you don't have a 0 training error? And then we're going to move to another important concept. Okay, we'll see that our previous sample complexity bound or generalization error bound, always assuming that your hypothesis space is finite, right? We use the log of size hypothesis space to represent the complexity of your algorithm, right? But what if your hypothesis space is infinite? Actually, many learning models, they use infinite hypothesis space, right? Even including linear classifiers, right? Because your weights are continuous, right? You have infinitely many choices, right? In that case, can you come out a proper measurement of the model complexity? Then we'll introduce such a measurement, which is called VC dimension. Right? VC dimension is based on is constructed based on this concept Shattuck. Okay. So before we proceed, right, let us just quickly review what we have discussed so far, right? We talk about PAC learnability, right? It basically says, okay, you don't need too many training examples to achieve a good generalizability with high chance, right? And we also talk about Occam's razor's principle, meaning that if you have several models which gives the same fitting to the data set, you're going to pick up the smallest, the simpler one, right? And we talked about the conclusion about computational learning theory when we assume that the classifier can guarantee to have zero training error. So here it just means it can always give the consistent prediction on the training set. Right? And we said that under this assumption, right, let H to be any hypothesis space, we claim that if the number of training example is bigger than this lower bound, then with probability at least 1 minus delta, a hypothesis H in the hypothesis space with zero training error will have the true error less than epsilon. Right? This is what we have previously showed, right? And to get those conclusions, right, we make two assumptions. First, the training and test examples come from the same distribution, right? This is reasonable, right? Although the data distribution might be unknown and super complex, but we're assuming that, okay, your training and test data are coming from the same distribution. And then another important assumption, which we're going to break today, is that for any concept, right, that's in empirical learning, right, or any target function, there is some function in the hypothesis space that is consistent with training set. Basically, it just means for any target function, you can find a function in the hypothesis space with zero training error, right? And this second assumption implies that your target function must belong to your hypothesis space, right? So C indicates the concept class, meaning that the family of target functions you want to learn, right? And big H is the hypothesis space from which your learning algorithm search, right? If you want to ensure that for any target function in C, and for any training set, you always find a hypothesis in your H, which can give zero training error, then you don't have any choice. You have to make sure that every concept in the concept class must be inside your H, right? Otherwise, suppose you got some target function here, you always construct some training example, which every member in big H cannot make a correct prediction, right? Then you cannot give zero training error. Right? Does it make sense? So that's our assumption, right? We have assumed the learning algorithm could find hypothesis space, which implies that your concept class, your target function family, are inside your hypothesis space. Of course, this is like too strong assumption. Why do you believe that your hypothesis space is large enough to contain every possible member in your concept family? So let us consider a more practical and weaker assumption. What if some target functions are outside my hypothesis space, right? What if we are trying to learn a concept F using hypothesis in big H, but F itself does not belong to H? So suppose here, right? That means the concept class C is not a subset of H. So this setting is called agnostic learning. Agnostic means that, okay, I actually don't know whether the target function is inside my hypothesis space. Then a natural question will be, can we still say something about sample complexity? Okay, I have a question regarding the setting here. So this is this is very fundamental, different, right? Previously, we assume okay, our hypothesis space is big enough, is strong enough, so that all possible target functions are inside my big H. Right? My only task is to find a strong and smart algorithm, is always locate that, right? Locate that target function inside my hypothesis space. But now I make a much weaker assumption, right? I assume that it is possible that the target function is outside my hypothesis space. In this case, I'm going to still look for some conclusion regarding sample complexity, generalization error. That's my basic setting. Right? Obviously, this setting is much more realistic than before, right? So, under this setting, can we guarantee the training error will be 0? No, right? Because your f, your target function could be outside, right? It is possible that you have some training set which any hypothesis in the hypothesis space H cannot give a correct prediction, right? And then you are no longer guaranteed. You will no longer guarantee you always get a 0 training error. Right? Our expectation will be we can find a hypothesis which has a small training, right? But it's not 0 training. Okay. So our goal should be to find a hypothesis in your hypothesis space, big H, that has a low training error, right? So remember, this is the definition of the training error. Right? That is the fraction of the training examples that are misclassified is low. And then in that case, we still want to find some guarantee that a hypothesis found by our algorithm, right, learning algorithm, with small training error, will have a good accuracy on sane examples. Right? That is, will have a good generalization performance. Right? And remember, the true error or the generalization error is defined as this, right? It's a probability that if your training data, if your test input comes from data distribution, you'll make a wrong prediction by your learned hypothesis H, right? Then the problem becomes, how can we use a small training error to bound the generalization error? That's the key idea of doing some inference on agnostic learning. Any questions so far? Yeah, I want everyone to feel comfortable about their logic, right? So first, we kind of get rid of the assumption that you got 0 training error. Right? We assume that you still have like training error, although it could be small, right? But we still want to use this small training error to bound or to estimate the possible generalization error. Right? We want that possible generalization error to be small as well. Right? Yeah, for example, if my target function is a quadratic function, but you use linear models to fit that, of course, no matter how well your linear classifiers are doing, right, it won't find the target function. Right? Do you want another example? No. Okay. Another question? But here, let me continue with that example, right? But here we won't give up our hope, right? We can see that, okay, if I got some training error to be small, like say 0.05, right? I still want to use this 0.05 to estimate the generalization error of my learned linear classifier. Even the target function is not linear, it's a quadratic function. But if I use my linear classifier to make prediction, I still have some generalization error, right? I want to ask me what's that generalization error will be. Okay. So, and then to estimate such a bound, or to bound such a generalization error according to the training error, right? What kind of tool shall we use? We will mainly use the so-called tail bounds. Okay? So what's tail bounds? It comes from statistics, right? So we know that, right? Usually, for a random variable, right? No matter what kind of distribution it follows, right? The random variables is more likely to be close to its mean, right? And the further away the random variable takes the value from the mean, the smaller the chance, right? This has been observed in many distributions like Gaussian, like student T, like whatever others, right? So know that, suppose the mean is 0, right? So know that, okay, under surrounding 0, you got much higher chance to take the value, right? But if you want to say, okay, what is the chance that a random variable takes the value to be much farther away from the mean, the chance is much lower, right? So tail bounds just tell you, okay, how can we bound the probability that a random variable takes value far away from the mean? It is used in hypothesis testing. I wouldn't say this is hypothesis testing. Hypothesis testing is saying, okay, if I got some 0 assumption, and right, hypothesis assumption that if it follows that, and if your observation appears to be a rare event, that won't happen, right? I'm going to reject my hypothesis, right? But yeah, they kind of have some similar flavor. But here we're not interested in whether we want to reject the hypothesis or not. Right? We're just interested in say, okay, if this random variable follows some distribution, what is the bound of its chance to take some value far away from its mean? It depends on the particular tail bounds you want to use, right? But in most of the cases, yeah. Many inequalities, they're assuming that we can find finite variance. Right? Okay, so now let us look at several instances, right? Bounding probabilities. Right? So the first one is called Markov inequality. Right? Suppose you are dealing with a non-negative random variable. Right? So we can bound that this non-negative random variable x, the probability it takes value bigger than a is upper bounded by the expectation of x over a. So you can see that the larger the a, the smaller the bound, right? The smaller the upper bound, that means the smaller the chance that you're going to take that value bigger than a. Right? The second one is called Chebyshev inequality, right? And here, we do need your random variable has some finite variance, right? So it just tells us, okay, if you got some random variable x who has mean mu and standard deviation sigma, then we can claim that the probability your x value is differ from the mean by k many standard deviations. This chance is no less than or no bigger than 1 over k squared. So you can see that the larger the k, that means the farther away your x takes value from the mean mu, right? And then the smaller this value, the smaller the bound. That means the smaller the probability. So any question regarding those instances? Right? Hopefully you can have a sense about this the meaning of those tail bounds, right? And these are just the two common use cases, but it's not the tail bounds we like to use in our case. Right? And what we want is we want to bound an average of random variables, not just a single random variable. Why? Because we'll see later, the training error essentially can be viewed as an average of random variables. Why? Because each training example are independent, identical distributed, right? My training error essentially is to look at a set of indicators, right? The indicator 1 means, okay, if your prediction for example 1 is correct or not. Indicator 2, if your prediction on example 2 is correct or not, and so on, right? And then you just average the summation, an average of those indicators. That's your training error, right? So essentially your training error is a random variable, and it's an average of a set of independent random variables. We'll go to that in math in details later, right? But here, let's just keep that in our mind, right? And to bound the average of random variables, right? The values of average of random variables, we use the so-called Hofstad's inequality. Right? So what is Hofstad's inequality? Right? Suppose I got a set of independent, identically distributed random variables, IID, right? X1 to Xm. I define P bar as the average of those M IID random variables. And P is the expectation of those random variables. Right? So remember, because X1 to Xm are IID, so the expectation of each random variable is the same. Right? And also P is not a random variable. P is just a constant, right? And P bar is a random variable because it's the average of X1 to Xm. Right? Then we claim that the probability that your expectation is epsilon away from average P bar is no less than this exponential term. It's e to the power of 2 minus 2m epsilon squared. No, it doesn't rely on that. You can use for any random variables, as long as it has a finite mean. Right. Right. So what can we observe from this bound? Any thought? Increase the probability. Oh, that means you're saying increasing m, right? Okay, yeah, correct, right? So first we can observe that the more random variables you average, that means the larger the m, the smaller the bound, right? So that means that the more IID random variables you average, the more you have put a constraint on the values of the average, right? In other words, it will be more likely to be close to the truth, to the mean, right? To the average, to the mean, to the expectation, right? And such decreasing is exponential. That means it decreases very, very fast. The bound decreases very fast, right? And meanwhile, the larger the distance epsilon, the smaller the bound, right? And also this bound decreases even faster, right? Exponentially and quadratic, right? So that means, okay, it's highly unlikely you got very, very far away from the true mean, right? That's what Hofstad's inequality tells us. Right? So any question regarding the meaning of the Hofstad's inequality? If you want to use central limit theory, you want to say what's the distribution of P bar, right? Right, it's approximately normal, but it's anyway using Hofstad's inequality is enough for. And if you want to say, okay, you want to characterize the distribution properties of P bar, yeah, of course we can do that, right? But here we just use this one, should be fine, right? And yeah, any other question? Then I agree with what you said. Right? Is it stronger? Right? Is it stronger? Okay, so but just let's keep this in our mind, right? So next we're gonna look at how we can apply Hofstad's inequality to our agnostic learning setting. So P here is the true mean, right? It's like you toss a coin, what is the probability that you see the heads, right? And the P bar is the empirical mean. So basically you can you toss a coin for 100 times independently, you just take an average, look at the portion of you see the heads, right? And in a concise way, we can see Hofstad's inequality tells us the empirical mean will not be too far from the true mean if there are many samples, right? Samples means here M, right? Number of samples. Right? So now let us contrast to our agnostic learning setting. We actually previously has just discussed, right? So the training error can be viewed as empirical estimate of the true error. Why? When we write down the training error, it'll be like this, right? We just look at, for every training example, if your prediction made by H is the same as the prediction made by the ground truth, right? So this is essentially a binary variable, right? 1 or 0, right? And because every training example is independent to each other, that's our basic assumption, right? That means those binary random variables are IID, identically independent distributed. And then we just take an average of these M random variables. That's our training error, right? So you can see that this is essentially an empirical mean, right? At the same time, we can look at the definition of the true error or the generalization error, right? The true error essentially is a probability that your prediction is wrong, right? Which can be viewed as the probability that your indicator binary random variable is 1, right? So remember, the binary variable, the expectation of a binary variable is the probability that binary variable is 1, right? So it reflects that your true error essentially is the mean of each binary variable, right? Then we can see that your true error is actually the true mean, right? Your training error is actually the empirical mean. Does it make sense? Any question at this point? Okay, great. And then we just replace P, the true mean, by our true error, and P bar, the empirical mean, by our training error. And that's it. Okay. So suppose we consider the true error, also known as generalization error, to be the true mean. Then the training error over the M examples is actually the empirical estimate of this true error, right? Then we can ask, what is the probability that the true error is more than epsilon away from the empirical error? And this is actually a straightforward application of the Hopf-Dynasty inequality, right? If you want to ask, okay, what is the chance that your true error is epsilon away from the training error? You just apply it. Right? Then we can see that this probability is upper bounded by this exponential term, right? Right. So next, right, we want to see, right? I want my true error to be not far away from the training error. Let's say if I can find the small training error, say the small training error is 0.05, right? I want my epsilon to be 0.01. That means that, okay, I want my true error to be less than 0.05 plus 0.01, right? So I want to see in what kind of conditions we can make sure this probability is small, right? Then what shall we do, right? We can set a number of training examples and to see if we can control this, right? That's the same strategy we have discussed previously, right? But before that, right, we need to first think about, right, the learning algorithm is trying to look for some best hypothesis in the whole hypothesis space, right? And actually, for general analysis, we cannot assume that we know how this algorithm will find that so-called best hypothesis, right? So we're going to relax this result, this Hopf-Dynasty inequality, to a general hypothesis space rather than just a single hypothesis, right? So then we're going to change our statement to be existence statement. What is the existence statement? The existence statement will be, okay, what is the probability that there exists a hypothesis in H whose true error is epsilon away from the training error? What's that bound? Right? If we can remember, we did the same thing for the consistent learner case, right? Right? We talk about for the particular hypothesis, what's the bound of the true error? What is the bound of the true error when given some probability, right? And then we talk about, okay, what if we want to change the bound for the existence of such a hypothesis whose true error is less than epsilon and so on, right? And we kind of apply the same strategy here, right? Because we don't know which particular hypothesis will be willed and found by our learning algorithm. So we kind of, that's why we kind of find a more general or more relaxed bound. That is, what is the probability that there exists a hypothesis who you think your whatever algorithm think is best, whose true error is epsilon away from the training error, right? And how we get that bound, we're going to use the same proof as we did before. We use the union bound. Right? So this existence statement can be viewed as the first hypothesis in your hypothesis space is more than epsilon away, or the second hypothesis in the hypothesis space is more than epsilon away, and right? And is upper bounded by H1 is more than epsilon away, H2 is plus the probability of H2 more than epsilon away plus the probability of H3 is more than epsilon away, right? So you can see that the existence statement will have such a probability bound, that is, it is upper bounded by the size of hypothesis space H times e to the power of minus 2 amps epsilon squared, right? It simply just adds up all the bounds for every possible hypothesis in your hypothesis space. Right? And then we want to play the same game as before, right? We want this probability to be smaller than some epsilon or some delta, right? Right? Because we have some high chance that your true error will be close to your training error. So how can we control that? We can set a threshold delta, right? Then we want to look at how do we set the number of training examples such that this chance is less than our threshold delta. The remaining will be just to solve this inequality in terms of m, right? Then we can claim that, we can derive that when m is bigger than this lower bound, then with probability at least 1 minus delta, your true error will be epsilon within epsilon away from the training error. Does it make sense? It's a little bit tedious in illustrating this, but the idea is like this. I want because I will okay, my true error is epsilon away from the training error is kind of bad thing, right? A bad event. I don't want that bad event to happen frequently. Right? I want to control the chance of that bad event to happen, so I set a delta, right? Then I just solve this bound less than or equal to my threshold delta, right? I found that, okay, as long as my number of training example is big enough, then this bad event to happen, the chance is smaller than my designated threshold delta. Any questions so far? Mm-hmm.
So the statement always that's your senior less is in a certain bound, in a certain distance from OSB.
Mm-hmm.
But you know OSB minus OSB. Is less than epsilon.
You can write it in another way. You can write it like, okay, error DH subtracted by error SH less than epsilon. Yeah. Yeah. So this, why do we use upper bound? You're asking for this? Yeah, because upper bound is more meaningful to us. You can try to construct some lower bound, but the lower bound is not.
way less than. Way less than.
If m is less than this, then you won't guarantee that, okay, this probability is less than delta, right? And here we just assume, okay, what's the minimum number of training examples you need to use to control the probability that your true error is too far away from the training error, right? That's why we use upper bound, right? If you have some lower bound here, and then you can still say anything, any guarantee on that, right? Want to put some strong guarantee on that. Right? Of course, like it is possible that because we use upper bound, we solve upper bound less than equal to delta, right? And that means, okay, as long as m is bigger than this, okay, that means the upper bound must be less than delta, and then we can guarantee that, okay, it must be, the chance must be less than delta, right? But yeah, it's possible that, okay, even m is smaller than this one, and it is still have some chance that this guy error dh is less than or equal to error sh. It's possible, but we want to put a more strong condition to ensure that, okay, in whichever case it will hold. Yeah. Any other question? Okay, so now we have a conclusion very similar to the conclusion we derived for consistent learner case, right? In our previous discussion, right? So agnostic learner makes no commitment as to whether f in H, the hypothesis space, and returns the hypothesis with least training error over the least m examples, right? But it can guarantee that if the number of training examples is bigger than this thing, right, then with probability at least 1 minus delta, the true error is not off by more than epsilon from the training error. So you can see that it actually bounds the distance or difference between the generalization error and the true error. Okay. So our previous discussion, we actually bound directly the generalization error, right? There's no, so in our previous case, we're saying, okay, if m is bigger than some bound, right, with high chance, the generalization error is directly less than or equal to some epsilon, right? But here, this just tell you the generalization error will not be epsilon away from the training error. So that means the generalization error contains the two parts, right? One is training error, one is a gap from the training error. Actually, the bound gap. This is reasonable because in agnostic learning, it won't guarantee zero training error, right? You can only say, okay, how far away my generalization error will be from the training error. Does it make sense? Right? So you can see that epsilon here indicates the difference between the generalization error and the training error, right? In other words, how much worse will the classifier be in the future than it is at the training time, right? And here, H, again, indicates the complexity of the learning algorithm, right? It also reflects or justifies the Occam's razor principle, right? So you can see that for the same epsilon, for the same probability level delta, right? The smaller hypothesis you choose, the smaller number of training example you require to control that probability, right? Okay. And if we switch epsilon m, we can obtain, because epsilon is the difference between the true error and the training error, right? We actually can obtain the so-called generalization error bound, right? The generalization error bound tells us if we have m examples, right, then with high probability, at least 1 minus delta, it is upper bounded by this guy. Right? It's upper bounded by square root of log size of hypothesis space plus logarithm 1 over delta. Delta is the some probability level you designate and divided by number of training examples. Right? So you can see that the larger the training data size, the smaller the bound. I mean, the smaller the gap between the generalization error and the training error, right? So now let us contrast the two learning settings we have discussed so far. The first one is a consistent learning, meaning that you can guarantee your training error is 0. Then we can derive that, which we have shown that previously, right? if your number of training examples is bigger than this lower bound, then your learned hypothesis will have the true error less than epsilon with at least 1 minus delta probability, right? And now for the agnostic learning, we're not directly bound. We're not directly bounding the generalization error. We're actually bounding the difference between the generalization error and the training error. And again, when your number of training example is bigger than this lower bound, we can see that with high probability, the difference is less than some epsilon. Right? Any question before we talk about next point? I mean, this whole proof or something is technically is straightforward, but you need to think more thoroughly when you apply this algorithm and not algorithm, the bound, and get clear about the meaning. Right? That's the most important thing. We won't ask you guys to show something in our final exam, whatever, right? But we do request you guys to understand what those bounds reflect. What's the meaning of that? Right? Okay, so looking at this two sample complexity bounds, right? We found that the learnability, right, depends on the log of the size of hypothesis space. As we discussed previously, right? We have yes solved everything, right? Because here we're going to assume that your hypothesis space is finite. Right? That's why you can put a logarithm of size of hypothesis space here, right? If your hypothesis space is infinite, then those bounds are not meaningful at all, right? The bounds are all infinity, right? Even for a simple linear classifiers, because the hypothesis space is infinite, right? And you cannot apply those bounds to analyze the behavior of linear classifiers. So then an important problem is that, okay, how can we address the measurement of the complexity for infinite hypothesis spaces? We can see that although we can construct many infinite hypothesis spaces, right? But some infinite hypothesis space is more expressive than others. Here we give some examples like rectangles, one hypothesis space, right? 17 size convex polygons, and general convex polygons. Right? So who can tell me which hypothesis space do you feel more expressive? Any thought? All those three hypothesis spaces are infinite, right? Because you do not know the coordinates of these rectangles or polygons, right? But which one do you believe is more expressive? 17 size? Okay, any other question? Any other answer? General. Okay, so first, 17 size convex polygon is a particular type of convex polygon, right? So that means every element in this 17 size convex polygon will be inside the general convex polygon, right? And also rectangle is just a 4-side convex polygon, right? So that means those rectangles are 17 size convex polygons are just a subset of general convex polygons, right? So we can definitely believe that the general convex polygons are the most expressive hypothesis space. And second example is a linear threshold function, is actual linear classifier versus a combination of linear classifier or combination of linear threshold units. Obviously, the second one is more expressive in that because every single linear threshold function can be viewed a combination of single linear threshold, right? So those examples give us a sense like why it is necessary to compare, to define additional metric about the complexity, right? So even the two hypotheses, both of them contain infinite number of hypotheses, right? Their expressivity can be different. So we need a measure of the expressiveness of an infinite hypothesis space other than its size, because its size is just infinity, right? So we can define all kinds of measures, but here we're gonna introduce the so-called Vapnik-Cherenkov dimension, shortly for VC dimension. So VC dimension provides such a measure. Right? So you can view it as a counterpart to the size of H. Right? So VC dimension provides an alternative measurement over the sample, over the complexity of hypothesis space. And correspondingly, we can also derive the sample complexity bounds in terms of VC dimension. Does it make sense? In other words, for infinite hypothesis space, right, we're gonna introduce a new measurement of the complexity, which we call VC dimension. Right? And next, we're going to talk about what's the definition of VC dimension. Right? But here, we just give some motivating example. Suppose our target function is axis parallel rectangle, right? And this rectangle classifier classifies all the points inside the rectangle as positive, outside as negative. Right? At the beginning, you might just be presented with like 3 examples here, right? And your learning algorithm might just find this one, right? The red one, of course, is far away from the target rectangle classifier, right? And you can keep adding more examples, right? You get a closer hypothesis to the true rectangle classifier, right? You can keep doing that, right? We expect that after adding more and more examples, my learned hypothesis will getting closer and closer to the true rectangle, right? Then the question will be, okay, can we answer the question, what is the number of those examples do we need to make the difference between the true rectangle and my learned hypothesis to be less than some threshold, right? That is sample complexity bound. And of course, my hypothesis space, which consists of all possible rectangles, are infinite, right? And my sample complexity bound should be finite. So we need some bound in terms of the measurement of the hypothesis space to illustrate that. Right? And that's why we're going to introduce the VC dimension, right? So the VC dimension is defined important concepts called shattering. I think we can stop here today. We're going to give some detailed discussion about shattering and VC dimension on next Tuesday.